Hi, I'm Jim Meekus. I'm a retired software developer and have a PhD in theoretical physics. I like science and I like telling stories. So I'm going to tell you some of my favorite stories from climate science. I think you'll enjoy them. I'd like to start with this guy.
Everybody knows who he is, but you may not know that he was a climate scientist. He's also my cousin. His grandparents were Peter and Mary Folger, Nantucket Quakers, and they were my great-great-great-great-great-great-great-grandparents. Franklin's climate story starts in 1768. Before the American Revolution, he was working for the Crown. He was deputy postmaster for the colonies, and he was stationed in London. His responsibility was to see that the mail got back and forth across the Atlantic as fast as possible. The trip took about 2 months, and Franklin learned that the New England captains could make the trip as much as 2 weeks faster than the English captains. He thought there must be something there he should know about. He brought up the question with his cousin, Timothy Folger, who was a New England whaling captain and happened to be in London at the time. Folger said, "Oh, sure, I know what that is. There's a stream of warm water that flows up the coast of North America. If you get into that, it really slows you down." "I've tried to explain that to the English captains," Folger said, "but they were too wise to be schooled by a simple American fisherman." So the next time Franklin crossed the Atlantic, he took along a thermometer to measure the water temperature. And being the way he was about things, he also invented a device to measure the temperature at depth. What he found was that there was indeed a well-defined band of warm water, and that the water underneath it was, deep down, was still cold. There was seaweed growing in the warm water. It was a plant called gulfweed. So Franklin gave the stream the name Gulf Stream, after the seaweed growing in it. With some more investigation, exploration, and discussion, Franklin and Folger developed a more detailed map of the Gulf Stream and published it, hoping that it would speed up transatlantic traffic. But the English captains continued to ignore him. For a long time it was thought that all copies of this map had been lost, but in 1978 2 copies were found in a French library. After the American Revolution and before the French Revolution, Franklin was the American ambassador to France. When Franklin left Paris for the last time in 1785, Joseph Fourier was a promising young mathematician. But Fourier got swept up in the ideals of the French Revolution. Liberty, equality, fraternity. Sounds better if you shout it in French, but my French isn't that good. When the revolution turned sour and became the Terror, Fourier tried to get out, but he was too deeply involved. He found himself in jail and in real danger of the guillotine. Fortunately, the guillotine got Robespierre first, and Fourier got away. After that, he became a trusted aide to Napoleon and spent several years in government. But when Napoleon returned from exile, Fourier had had enough of politics and wanted to focus on his math and science. So when Napoleon marched into Grenoble through one gate, Fourier fled through another. Turned out to be a good call. The return from exile didn't last very long. Fourier's math and science focused on heat transfer. He developed some equations for heat transfer that are still valuable today. By 1822, he'd gotten far enough with his theories that he was looking around for practical case studies to try it out on. One of the case studies that he considered was the Earth. He thought that since the Earth's climate seemed to be stable, that the amount of heat the Earth received from the Sun should equal the amount of heat it radiated back into space. So he calculated these 2 quantities by independent methods, the amount coming in and the amount of heat going out, expecting them to turn out equal. What he found was that in order for the quantities to be equal, for the Earth to be in equilibrium, it should be a frozen ice ball. He speculated about several possible explanations for the discrepancy. including the idea that maybe somehow the air acted as a blanket holding in some of the heat. One other thing I want to tell you about Fourier's life. Do any of you know somebody who has odd ideas about health? Fourier's life would be a cautionary tale for them. His idea was that you could stay healthy by keeping the body wrapped in blankets whenever possible. Remember, it's all about heat transfer. He died in his home at the age of 62 when he tripped on his blanket and fell down the stairs. This is Louis Agassiz, a Swiss naturalist. He became well known in geology for his studies of fish fossils. Sounds pretty boring, but actually fish fossils are very important to geologists, and still are, because if you find the same species of fish in two different rock layers, you know that they were laid down about the same time. It's a dating method. During Fourier's field trips in the Alps, some of the locals pointed out to him evidence that the glaciers had at some time in the past been much more extensive than they were then. As he continued his travels, he became more and more aware of the evidence of past glaciation. U-shaped valleys, deep scratches in rock walls, erratic boulders, moraines, began seeing them everywhere. He thought further about this and developed it into the idea that maybe sometime in the past northern Europe had been covered in ice. He gave a talk on the theory to the Swiss Naturalist Society. Wasn't well received. They booed and hissed and threw things at him. He made a trip to Scotland and saw similar evidence, gave a similar lecture. The Edinburgh Geological Society passed a resolution declaring that Scotland had never been covered in ice. Agassiz wasn't a nice man, and he didn't take kindly to criticism and rejection. When he traveled to America, saw similar evidence, gave his lecture again, he was warmly received and got to hang out with all the leading intellectuals. Thinking that he was finally getting the recognition he deserved, he stayed and became an American. His wife and family never followed. I can't help thinking that his wife may have been glad to see him go. He was so highly regarded in American geological circles that there was a statue of him on the facade of the Stanford University Geology building. In the 1906 earthquake, the statue fell from the building. A joker at the time said, Agassiz was great in the abstract, but not so great in the concrete. John Tyndall, Fellow of the Royal Society, Professor of Natural History at the Royal Institution. Despite the stuffy-looking beard and titles, he was a great popularizer of science. He wrote books about science for young people, gave lectures that were very popular. During his field trips in Europe, he became interested in mountaineering. He was a member of the first team to scale the Matterhorn. Actually, mountaineering became quite a fad in the late 19th century. Even the ladies engaged in it, without, however, giving up their Victorian fashions. John Tyndall was involved in a lot of different investigations. The one that's interesting to us was his measurements of heat absorption by gases. This is a diagram of the apparatus he used. Particular interest was his measurement of the heat absorption by carbon dioxide. He found, in fact, that carbon dioxide was opaque to infrared radiation. In other words, it absorbed heat rather than passing it through. That was Fourier's air blanket. It's the carbon dioxide in the atmosphere that keeps the Earth warm, keeps it from being a frozen ice ball by holding in the heat. Svante Arrhenius was a child prodigy. He learned to read at the age of 3, taught himself arithmetic by watching over his father's shoulder as his father kept the account books. His college career was kind of rocky because he was smarter than most of his professors, and he knew it. When it came time to defend his PhD dissertation, it didn't go very well because one of the professors was somebody that he'd badly snubbed. But he got through it. The dissertation was 150 pages of new ideas about physical chemistry. Eventually the work earned him a Nobel Prize, much to the chagrin of his professor, I'm sure. In 1896, Arrhenius suggested that industrial carbon dioxide might increase the Earth's temperature. He thought it would take centuries, and he thought warming up Sweden by a few degrees was a darn good idea. But he discussed the question with a colleague, Arvid Hugboom, who had been studying natural processes involving carbon dioxide. Hugboom calculated the rate that the industrial activity of the day was putting carbon dioxide into the atmosphere. They were startled to find that it was on the same scale as the natural exchange of carbon dioxide between the atmosphere and the Earth and ocean. That was 1896, over a century ago. Let's take a little digression here and talk about heat absorption and retention. Suppose you park your car in the sun. It'll get hot inside, you know that. But let's suppose you want to make it even hotter. Maybe you need to melt a Hershey bar or something, whatever. What are a couple of things you could do to make it hotter inside the car? Well, one thing you could do is roll up the windows, because that would trap the heat inside instead of letting it out. Another thing you could do is paint the car black, because then it would absorb the heat from the sun faster. Well, these two factors are also factors in the Earth's temperature control. As we put more carbon dioxide into the atmosphere, we're rolling up the windows, in effect. We're trapping the heat in the Earth's system. And as northern ice fields and snow melt, they reveal the dark Earth underneath and make the Earth overall darker so that it absorbs solar heat faster. This, I think, is the most charming of the stories. Milutin Milankovitch was a Serbian mathematician. He was born in Austria, educated in Vienna, moved to Serbia for his working career. In 1914 he got married. For their honeymoon he took his bride to his native village in Austria. They say timing is everything. Timing was certainly everything in this case. While they were there, Archduke Ferdinand was assassinated and the First World War broke out. The Austrian army arrested Milankovitch as a Serbian citizen and threw him in jail. Fortunately, his new bride was no wallflower. She charged off to Vienna, rounded up some of his colleagues and mentors, and used their influence to get him released from jail to house arrest. So he spent the entire First World War under house arrest. Not a bad deal at all. Many of Europe's best young minds were lost in the trench warfare. But Milankovitch's problem was how to pass the time, as the weeks and months and years as the war went on. Well, he turned the problem into an opportunity. He had a project he'd been wanting to work on, and now he finally had time to work on it. During the 19th century, the Ice Ages had come to be accepted science, but nobody could explain why they happened. Several theories had been proposed, and they'd all been shot down by one observation or another. Milankovitch's idea was that the Ice Ages have been caused by changes in the solar input because of variations in the Earth's orbit around the Sun. And he proposed that these changes in solar input caused the Ice Ages. So he calculated the Earth's orbit in exquisite detail, taking into account precession and the elliptic shape of the orbit and the gravitational influence of other planets. No calculator, no computer, just reams and reams of paper. The result of all this calculating was a graph of the variation of the solar input over the last 400,000 years. So he published this data and proposed that it was an explanation for the Ice Ages. The idea kind of fell flat at the time because the variations in solar input were fairly small, and nobody could believe that these little variations in solar input could have such vast consequences as to cover the Earth with ice. It wasn't until the 1970s that real data began to come in about the Earth's actual temperature history. This is the Russian research station at Vostok in the Antarctic. The United States and Europe operate similar research stations on Greenland. What they do at these research stations is drill down through the ice all the way to the bedrock. Miles, literally miles of ice. They pull out ice cores, An ice core is a cylinder of ice a few inches in diameter and about a meter long. There are bubbles of air trapped in the ice which contain samples of the Earth's atmosphere at the time the ice was laid down. So scientists can extract a lot of information from these samples of ancient atmosphere, the temperature and a lot of other things. Turns out that when you make a graph of the Earth's temperature history, as derived from these ice cores, lo and behold, it has a high correlation with the Milankovitch cycles. So the variations in solar input from the orbital changes must have caused the ice ages. But the question remains, how could these small changes in input have such huge consequences? Well, the answer is feedback, because the small changes in heat made changes in other circumstances that amplified the changes in temperature. Let's take a look at some samples of feedback. This is ice floating in the Arctic Ocean. As the Arctic Ocean gets warmer, the ice melts and reveals more of the dark water underneath. The ice reflects solar heat, the dark water absorbs solar heat. So the warmer it gets, the faster it warms. This is Siberian permafrost. The small circles are ponds of meltwater. When permafrost melts, methane is released, and methane is a more potent greenhouse gas than carbon dioxide. All over Russia, Canada, and Alaska, permafrost is melting and releasing methane. There are huge deposits of methane under the oceans, trapped there by cold and pressure. Methane is a fossil fuel, just like coal and oil. The only difference is this methane doesn't need an industrial process to release it. All it needs is warmth. Russian researchers have already seen methane bubbling out to the Arctic Ocean off their north coast. As northern forests dry out from heat and drought, they become more susceptible to forest fires. When a forest burns, the carbon that's trapped in its wood is turned into carbon dioxide and released into the atmosphere, increasing the greenhouse effect. This is an interesting example of feedback, subtler and, we hope, longer term. This is an elevation map of Greenland. The highest point in Greenland is over 12,000 feet above sea level. It's very cold at that elevation, as you know. But as the ice sheet melts, more and more of it is exposed at lower altitudes to warmer air. So the faster it melts, the faster it melts. Dave Keeling, as a young man, loved camping in the California mountains. So he wanted to go into a scientific study that would allow him to do his field work outdoors. He got interested in atmospheric chemistry, got interested in the question of measuring carbon dioxide in the atmosphere. You might say he became obsessed with measuring carbon dioxide. Arrhenius and Hugboom had tried to measure atmospheric carbon dioxide and failed. Their instruments weren't very good, and their measurements varied depending on which way the wind was blowing. During his postdoctoral work, Keeling developed an instrument that could measure carbon dioxide reliably and accurately. We talk now about parts per million. His instrument could measure carbon dioxide with an accuracy of parts per billion. For his first field trials, he went camping in the Big Sur with his wife and infant son. He got some good measurements, but they still varied depending on which way the wind was blowing, whether it was coming from highways or industrial activity or the woods. So he needed to go to a place where there wouldn't be any human activity to affect the measurements. His big break came in the International Geophysical Year of 1957-58. There was a lot of grant money available for measuring all kinds of things about the Earth. He got a grant to take his instruments to the top of Mauna Loa in Hawaii, 10,000 feet above the Pacific Ocean and well isolated from everything going on in the human world. He began getting some measurements, accurate measurements, consistent measurements. And during the second year, he saw that there was a year-over-year increase in carbon dioxide. The short cycles that you see here are seasonal, variations depending on the rate of plant growth in the northern hemisphere. The third year confirmed that there was a year-over-year change. Fourth year, even more. In 1964, his funding ran out, and he was unable to make some needed repairs to the instruments. But by that time, the scientific world had recognized that the data he was publishing was important, and there was an outcry, and his funding was quickly restored. So we went on getting measurements, and finally today we have what we call the Keeling curve, showing carbon dioxide in the atmosphere from his earliest measurements in the 1950s up through 2015 in this graph. Now tell me, look at the upper tip of that graph. Can you see any result from the efforts we've been making to reduce carbon dioxide emissions? You can't. It's not there. We haven't made a dent in the problem. This is from a Department of Agriculture brochure in 1947, urging housewives to use lots of DDT in their kitchen to control insects. Enter Rachel Carson. She was not a climate scientist, she was a marine biologist. She happened to have a tremendous literary skill. She'd already written 2 popular books, The Edge of the Sea and The Sea Around Us, about her work in marine biology. She saw the consequences of DDT and other industrial chemicals in the environment and became alarmed. And she used her literary skills to raise the alarm publicly with her book, Silent Spring. The public was so aroused by her book that she testified to Congress on the subject. Congress listened because the public was concerned, and Congress acted. A lot of good environmental legislation was passed, which we are still benefiting from today. By the way, when she testified to Congress, she was already dying of breast cancer. Now, I want to draw a line at this point. Everything I've told you up to this point has been established science. No question about it. The Earth is getting warmer. Warmth is caused by greenhouse chemicals in the atmosphere, and those chemicals are there as a result of human activity. All that is given, widely accepted, no real question about it. I have a few more scientists I want to tell you about, but their work is different. It's leading edge work. They are trying to figure out how, when, and where the consequences of this warming Earth are going to hit. And there are still a lot of uncertainty in every aspect of that. Climate change deniers will try to use the uncertainty of this leading edge science to cast doubt on the established science. Don't let them get away with that. This is Wally Brooker. As a child, he was dyslexic, a poor student, a poor reader, social misfit, bad taste in practical jokes. If you know a young person who's dyslexic and you want some encouragement about their potential, take a look at Wally Brooker. He is now a professor of earth sciences at Columbia University, has published over 450 papers and written 7 books. Brooker's science had to do with oceanography. Now, this is a modern version of Benjamin Franklin's Gulf Stream map. His map is this little loop over here. All the rest of this is global circulation of water. The red line is warm water from the Pacific Ocean through the Indian Ocean and up into the North Atlantic. The blue line is returning cold water from the Atlantic back through the Indian Ocean and up again into the North Pacific. What Brooker found was that within this global circulation was the answer to a question that had been puzzling scientists ever since the data came out from the ice cores in Antarctica and Greenland, because that temperature history showed that there were points where the Earth's temperature changed very suddenly. Geologically, sudden means a million years or a few thousand years, but these were changes that took place in less than a decade. And Brooker was able to show that in some cases these sudden changes had been the result of changes in the mode of circulation of this global conveyor belt. A familiar example is that if this northern loop here closed off further south instead of going all the way up to the North Atlantic, it would stop delivering heat to northern Europe, and northern Europe would experience a serious cold wave. By the way, since the heat has to go somewhere, if it didn't get carried up to northern Europe, then it would be left at the mid-latitudes and would contribute to the warming in East Africa and southern North America. James Hansen was at one time NASA's top climate scientist. His study had to do with the relationship between atmospheric carbon dioxide and Earth's temperature. He believed that there should be a straightforward numerical relationship, that you should be able to find a proportionality constant that would say if you put this much carbon dioxide into the atmosphere, it will result in this much increase in the Earth's temperature. In fact, all public discussions of climate change and attempts to deal with it are based on that idea. Hansen's early research alarmed him so much that he testified to Congress in 1988 on the subject. It happened to be a warm day in Washington, D.C., which helped the congressman focus on what he was saying. They listened, they heard him, they understood, and they acted. Several climate-related bills were introduced into Congress. The oil and gas lobbies reacted, and all of those bills were defeated. Nothing happened. Hansen wrote a book called Storms of My Grandchildren, and eventually joined the activists. Was arrested several times demonstrating with them in front of the White House. This is Jennifer Francis. She went to college to be a dentist. After 3 years of pre-dental school, she dropped out to join her husband sailing around the world in their sailboat. They spent 5 years exploring the world. They went to Antarctica, to the Arctic, all the oceans. One thing that she learned during these travels was that weather forecasting for the Arctic is really, really bad. So when she went back to college, she resolved to become a meteorologist instead of a dentist. One of her advisors pointed out to her that she could probably contribute more to the problem by gathering better data in the Arctic rather than trying to make better forecasts out of the available data. So she became a climatologist with research focusing on the Arctic. When the northern Great Plains began experiencing periods of deep cold and other extended periods of high temperatures, Jennifer Francis was able to propose an explanation. Her explanation had to do with the jet streams. The jet stream is a high-altitude river of air flowing around the globe. It's powered by the difference in temperature between the polar regions and the mid-latitudes. And it outlines the division between the northern polar air and the mid-latitude air. What Professor Francis pointed out was that the Arctic is warming faster than the rest of the globe, and so the temperature difference is decreasing. As the temperature difference decreases, there's less power to drive the jet stream, and so the jet stream is slowing down. Now, you know what happens to a river when it flows across a flat plain without much gravity to drive it. It flows slowly and it meanders and it forms loops and waves. And that's what's happening to the jet stream. It's moving slowly is forming loops. Now if you happen to be stuck on the north side of one of these loops, you're going to have Arctic air, and it's going to stay cold until the jet stream gets around to moving on. If you're stuck on the south side of one of these loops, you're going to have warmer mid-latitude air, and it's not going to change until the jet stream waves get moving on. Well, what did we learn? I'd like to run through this again briefly. I've presented these scientists in chronological order, more or less, but there are some threads that we can follow through them, and I'd like to try and pull out a couple of those threads. Agassiz taught us that the climate is not a constant. The relatively benign temperatures that mankind has used for the last 10,000 years to develop modern civilization is not a given. It doesn't have to be that way. Milankovitch showed us that the huge changes in the Earth's climate can result when feedback amplifies small changes. Brooker showed that the Earth's climate is controlled by switches, not dials. As he sometimes put it, Earth's climate is a raging beast, and we're poking it with sticks. Jennifer Francis taught us that this isn't just about polar bears, it's about us. What happens in the Arctic doesn't stay in the Arctic. Joseph Fourier is often credited with being the first to suggest that the atmosphere might act as a blanket holding in heat. In fact, I think he made a more fundamental contribution with the simple idea of viewing the Earth as a heat reservoir whose temperature is controlled by the balance between heat flowing in and heat flowing out. We are trapping the heat that should be flowing out, and we're increasing the amount of heat flowing in by changes in the darkness of the Earth's surface. So by changing this balance, we're changing the temperature. Tyndall simply identified the air blanket as being carbon dioxide. Arrhenius is credited with being the first to suggest that industrial carbon dioxide might increase the Earth's temperature. In fact, again, he and Hoogboom made a more significant observation, I think, when they found that industrial carbon dioxide was entering the atmosphere at a rate comparable to the rate that the natural exchange of carbon dioxide. In other words, human activity can rival natural processes in scale. We are no longer just observers in the Earth, we are participants in affecting the actual outcome of things. Keeling gave us rigorous data about the scale of human activities, the rate at which we are putting carbon dioxide into the atmosphere. Hansen tried to put a number on the relationship of CO2 to temperature, but in fact, if you read his recent writings, you'll find that he is coming around to Brooker's view that it is not a proportional relationship. It's nonlinear. In other words, things can change suddenly, not proportionately. Fourier withdrew from politics to focus on his science and math. Hansen went the other way. He moved from science to politics. Rachel Carson moved from science and through literature to politics.
There's a book called 100 Scientists Who Changed the World. How many of the scientists I've told you about do you think are in that book? Well, the answer is one, Benjamin Franklin. And he's there for his contributions to electricity, nothing to do with the Gulf Stream. I think the title of the book is wrong. Scientists don't change the world. Scientists change your understanding of the world. Then it's up to society to decide how to respond to that new understanding. Edward Jenner changed our understanding of disease. Society used that new understanding to wipe out the scourge of smallpox. Now we're on the verge of wiping out polio. Albert Einstein changed our understanding of energy in the atom. Society used that information to make a terrible bomb and wipe out whole cities. If any scientist could be said to have changed the world, it would have to be Rachel Carson. She gathered the data, saw its meaning, and used her literary skills to compel society to respond appropriately. Climate science hasn't found its Rachel Carson yet. We have Bill McKibben, who makes nice speeches. We have Al Gore, who makes nice movies. But so far they have not inspired society to respond. That needs to change.
What can we do about it? Can we do anything about it? Well, here's Dubai. The city of Dubai issued a bid request for a 100 megawatt solar farm. The three lowest bids came in at under 4 cents a kilowatt hour. You and I are paying 10 to 13 cents a kilowatt hour. It doesn't have to be that way. Germany is making a serious effort to convert to renewable energy. As you can see from this graph, they're making real progress. About a third of their energy now is from renewable sources. China has 1.5 times as much installed solar as the United States has, and they're adding to it at twice the rate we are. Professor Mark Jacobson of Stanford University has published an interesting study. He has shown for every state in the Union a mix of renewable sources that could make that state entirely renewable. And if every state can be renewable, then certainly America can. Each state has different resources available to it, and so for each state there's a different mix of renewables that are appropriate to it. In Washington State, Jacobson's mix relies heavily on hydropower because we have rivers and mountains and flowing streams. But there are several other sources contributing to it also. This is Jacobson's solution for the state of Florida. It relies heavily on solar, as you can imagine. There's no hydro, but there are other sources as well as solar. There's another interesting thing about this study. For each state, he shows not only what an appropriate mix of renewable energy resources might be, he also shows how much money would be saved and how many jobs would be created. What can you do personally? Well, you can spend a bunch of money and put solar panels on your house. You can spend another bunch of money and drive an electric vehicle. Or you can save money and eat vegetarian, because animal products, meat and dairy, are major contributors to greenhouse gases and climate change. Some say they're a bigger factor than transportation. You can encourage your institution to do the right thing. Solar panels on the roofs of lots of buildings. Divest the investment funds from fossil fuel investments. Install electric vehicle charging stations so that employees, faculty, students, whoever can more easily drive an electric vehicle to the campus. And vote. Before you vote for any candidate, make sure that they understand climate change and are willing to act on it. So that's all. Now I'm ready for questions and comments.